picture is about 500 micrometer. So it's a quasi macro scale observation. At time 0, we have a total breakup of the nanotube, and you can see with the time structuration of the nanotube. And this is a macro scale nanostructure. Of course, you have maybe at the micro scale some aggregations, but you have this phenomenon. So you can see that, of course, you have a strong difference from a rheological point of view. In this condition, where the network is totally break, you have a viscoelastic liquid, and here, when we have a network, you have an elastic behavior at the low frequency of the suspension of nanotube. We found more details about this study in our last publication. So about the conclusion, the critical transition of semi-dilute regime is close to the Doyle-Edwards theory. We have a strong deviation of the theory above this transition, and the Brownian motion of nanotube is the dominant regime in semi-dilute condition, but we have a clustering phenomenon of this nanotube for the concentration higher than the 1.16. And the main interesting result is the following, that the kinetic of the cluster formation depends on the dynamic strain critical deformation, because we have a competition between aggregation and breakup. So I have put here a last sentence. This one said that people said one might question the quality of nanotube dispersion of many famous experiments in last decade. Yes, it's a real question. What is the dispersion of a nanotube when you are performing some rheological experiment? And I would say that unfortunately everybody is wrong, and fortunately everybody is right. But it's very difficult actually to compare the results between different authors, because it's never the same nanotube, never the same suspension, it's never the same pressure or the same elongation of process. So it's very complicated. And I choose to, if you are interested in the in the rheology of nanotube, the last publication of OB published in Rheologica, which is a review on the influence of shear on the rheology of nanotube. And sometimes this is a picture from steady shear flow. You can see here a strong agglomeration of nanotube. Okay, it is because you see here the scale is about 1 millimeter, so you have a lot of strong agglomeration. So I can ask this question to myself: I am wrong or I am right? So I'm going back to my slide rapidly. Sorry. This is right. This is right. This is right. This is right. Right. And this, maybe it's wrong. Why? Because the time, the rest time is about 48 hours, and if you consider this experiment, you can see here that at 50 hours, I'm not at the equilibrium. So during this experiment, actually, I have still the structuration or the aggregation of nanotube is not over in the present case. But as the time is very long, about 100 hours, the curve is right. But it's right under this specific condition. Thank you very much for your attention.
Thank you very much, Philippe. I think this was a very good talk, showing us limitations and also what you really have to look at. It's open for discussion. Any questions? Yes, there's one in the back too.
Hello. What was the temperature range used in these rheology measurements? Sorry? The temperature used in rheology measurement.
Temperature.
The temperature is the room temperature, is about 25 degrees, so 22 degrees.
And is there any minimum concentration at which this network formation would take place? The minimum concentration of nanotubes?
Sorry,
The concentration? The concentration here is about...
My question is there any minimum concentration at which a network formation?
Is there a minimum? Yes, it's a good question. At 0.1%, just at the critical concentration between semi-dilute and semi-dilute geology, we observe this phenomenon also.
Thank you.
But at a higher concentration, at 0.5, you don't observe this phenomenon because the network, you cannot break down the network, and this phenomenon is observed just below 0.3% of nanotube.
Any other questions? I think you made it clear. There's one more, please.
Yeah. Why you have correlation between the mechanical property and transport property, means charge transport? Yes. You are establishing a correlation between viscoelastic properties and transport properties. How comes? How is this? What is the mechanism to establish that correlation?
It is a strong debate in the literature how we can compare viscoelastic behavior with electrical behavior. So when you have clustering of a nanotube, you have a variation of the viscoelastic property because this fluctuation is governing the viscoelastic behavior. And of course, when you have clustering, you have more contacts between nanotubes, so you have a better conductivity of your suspension. But I'm not an expert. I don't want to debate with people who are working on this subject because it is rather complicated.
Thank you.
Okay, one quick question, please. Okay.
Do you know how the suspension of nanotubes behave compared to suspension of other nanofillers like nanoclay? Or I remember work from the group of Pierre Caro, and he was studying nanotube suspension and formation of structure.
Yes and no. The main difference with clay is the aspect ratio. And this particular behavior comes from the aspect ratio and this mechanism of aggregation. In clay suspension, the aspect ratio is smaller, and I'm not sure that we have this kind of behavior, or at least it's less pronounced that we observe here.
Yeah, please.
Have you checked if there is any difference in the conductivity along the sharing directions and perpendicular to the sharing directions? If there is any anisotropy? Okay.
I invited you to
Okay.
This is the volume conductivity. This is the volume conductivity.
Good. I think we have to stop here. Thank you very much.
Thank you.
Hand over to my co-chair, Prof.